Okay, we made it back, even after a 3-day weekend where you start contemplating, like, should I go back? It's pretty nice to not do anything. Did you break anything yet? Are there any, like, big errors? It's like something happened, you changed one little thing, and now nothing works. Try more stuff. You gotta push a little bit further. Like break things more often. So you learn through fixing, like building, creating, doing stuff. What are we working on today? Other questions about like reading so far, like material? Yeah.
I have a question on one of the, I think it was module 1, part 3, where it talked about round off.
Okay.
And understanding the difference like the 64-bit to 32-bit.
Yeah.
Can you
okay.
explain that better? Just having trouble understanding it.
All right, so I'll come down. So truncation versus round off. Do you know difference between truncation error, round off error? Does anyone know like what that would be? Not sure yet. Which one do you think is, like if you're doing a finite element model, do you think truncation error is a bigger problem or round off error is a bigger problem? Round off, maybe? Who says like round off? You don't have to know, like this isn't a test or anything, but like who says finite elements round off is your biggest enemy versus truncation error? So round off, couple yes. Who says truncation error is your biggest enemy? Oh, the same people. You wanted to change your answer before? Truncation or round off? Which one are you? Truncation? And then a lot of other people are just afraid to admit like that you might be wrong about something that you've never studied before in your life. This is the first time you're seeing it. It's okay to be wrong. So something like finite element models, your biggest enemy is your truncation error, because what you're doing with and this is like one example of a truncation error. I'm taking a smooth function, like stress is some kind of smooth function throughout the entire volume of the material, but I'm going to truncate that and say that it's a whole bunch of straight lines, or maybe like parabolas or something, but somehow I'm truncating the exact solution that is some kind of like, maybe it's an infinite order polynomial, but I'm going to say it's a first order polynomial from one point to the other. So truncation error is like, you take a function and you just approximate it. And as engineers, we do this all the time. And you can see like truncation error for small, if you have really small like boundaries on your truncation error, then everything's good. And we do this for like steam tables in thermodynamics. That's what linear interpolation is. We're saying like, we know the point here, we know the point there. We can approximate it with a truncation. We introduce truncation error by approximating it as a straight line, but it's no big deal, like, because it's probably going to be well within any kind of error that we would have. So truncation error is usually what we're fighting against. We're trying to make our models more accurate with like higher and higher order things, or add more and more nodes. Like somehow we're fighting that truncation error. So then the other error is this round off error. What do you think a round off error would be? Yeah.
Every time you calculate a step, you would round it to a certain decimal point, and then you have now a rounded number calculating the next step.
Yeah. So rounding and it's a rounding error that if you think about it as like if you have a ruler that can only measure 1 millimeter increments, then every time you measure something, you've always got to say it's 4 or 5 millimeters. And as you add those lengths together, sometimes that'll add or subtract a millimeter here and there, or half a millimeter, right? So we have the same problem with bits whenever we're storing things in a computer. Have you heard that term, bits? Bits and bytes. What's a byte versus a bit? Byte. Sorry? A byte could be 8 bits, yeah. A byte could be 8 bits. What else could a byte be? B-Y-T-E, not like a... What else could a byte be? It could be 8 bits. That's like Nintendo. Nintendo was always, every byte was 8 bits, the original NES. Now, Nintendo Switch is all, it's not 8-bit anymore. Although you can still use an emulator to play 8-bit games. So right now there's 2 main things that we use, either 64-bit or 32-bit. And those are, 1 byte is like a 64-bit number or string or something, and 32 bits is half as many bits per byte. Bit per byte, yeah. And what we end up with, like bit 64 versus 32. Like we can see like the exact first 27 digits of pi are kind of listed out here. For the most part, 64, 32, there's no difference in pi. And for 99.99% of all of your calculations, it's going to be 64, 32, it doesn't matter. But as you get deeper and deeper into these digits, 64-bit has a different approximation for pi than 32-bit, which is different from the exact value of pi. And that's just because we only have so many powers of 2 that we can, because every bit is a 2 to the power of something, of -1, -2, -3. And you can only store it so well. If you think about it as like that ruler, you only have so many like measurement places in your ruler. You can only, with 32, you've got half as many spots. And it would be nice if it was like 10 to the power things, because that's kind of usually how we think about decimal spots. But here it's 2 to the negative, like 32, I think, is like the smallest. Yeah, 2 to the negative 52, sorry, that's 64-bit. And then I think it's like 2 to the negative 20 something, like 26 or 27 for 32-bit. That's like as small of a change as you can measure with a number. So that's like, once you get to the point where you have like 10 to the negative 15 answers, the computer can't tell the difference between 0 and 10 to the negative 16. It's just, you can't. So if you're doing a finite element simulation, you keep reducing the error, and now it's giving you like 1 times 10 to the negative 16, 3 times 10 to the negative 16. You've already hit the floor. Like you're not going to get any more accurate. The computer just can't measure it anymore. I don't know if that helps with your original question. What else are we working on today? Can I check in, see what people are, see what individual things come up? Then we'll go from there. Oh, yeah.
I have a general question about, like, if we save, like, let's say home font, if we save it, will we be able to reopen it and we'll have all that information?
Yeah, so now that we're running on NanoHub, everything that you do when it gets saved, it's all there. Yeah, so you can. So I'm gonna open, like if you click on this Jupyter thing at the top left, oh, brings you here. Oh, there we go. All right, so if you click on, sorry, different process. I'm used to clicking this like Jupyter icon, but if you say File, Open from here, it brings you into like the main browser window of like what files you have. All those are just in your NanoHub account. So as long as you have access to NanoHub, you'll always have these files and the work that you did. And if you ever need to, let's go here. Like if you're working on the homework and you delete like one of these cells or something, you can always download this like MD file again. Oh, didn't download it. Save link add? No, I wanted to save it. I mean, I guess we could do that. Copy everything and paste it in there. Seems like a I should save it, huh? But you can always like copy stuff from the website and get it back if you need to like start from a clean slate, or you just want to copy and paste over like the original things. But all the source code is there, and it's even in your GitHub repository now because you made a fork of it. But I feel like it should have just downloaded that. I guess I could say Control S. Yeah. If you do Control S, then it'll download it. Homework 1, MD. And then we could do what I was thinking of like upload, downloads, homework 1 MD. And this one's asking me, do I want to overwrite homework 1? And I'll just overwrite it. So I start from scratch. All right, I'll check in and see what people are up to. Yeah.
There's a convention here versus to start on here, pick one, and then say variable one.
Yeah.
Is it convention to comment the line above it or to the right of it? If I want to say this is fine, you can get
yeah, so it depends on how long the comment is. Like usually, it depends on who's like formatting follow. Like a lot of times, 80 characters is the general. That's how long the line should be. So if you're just commenting like comment CM2, then that's great. But it's right next to it. But if you have comment volume is centimeters cubed, then it's this long line. So yes, cool. That would be the That's how central semantic question. Yeah, because it's the same thing. Yeah, yeah. But like we can just list. Usually when someone says like so many pounds per interview, they're talking about force. You put it on a scale. It's gonna create that much force on the scale. So the density to that's overfar. We'd be trying to divide by 32.2 to get down fast. That would be slugs. Yeah. So you could say like this is how many slugs per each cube, and slugs. Yeah. I mean, if you want. All right. So here. So after a quick tour of like what we're working on. All right, so our first step is like, what is the volume of the box? We know the box is 31 pounds. So the question was coming up of unit analysis of like, is this 31-pound force? Is this 31-pound mass? And I guess it's just part of the system that we live in here in the U.S. of having like our like unit of our units are. Force is the base unit. Mass is a derived unit, which is a little weird, but whatever. And thermodynamics confuses this even further because they say that there is such thing as a pound mass, which is, but then there's this like imaginary 32.2 thing that somehow gets involved. I don't like that. So if you're gonna use like mass in this unit system, then pounds is always pound force, and mass then becomes slugs, like a pound per g, which, and again, it's all kind of weird, but it's totally fine to just say like it's so many pounds per inches cubed. Like that's very measurable and very repeatable. Like that, it's fine. If you want it like, but density is always mass per volume, then like you can do it your way, but 31 over volume is. And so while we're doing this, why don't we do this? Show you some fancy ways of printing things with strings. So I can give it like, hey, print this string for me. Most of it is just going to be whatever I typed, but when I put those squiggly brackets in, now it's going to take that dot format and throw it into that squiggly bracket. And this is the reason I'm showing that is like whatever units you want to use. If you want to convert everything into meters and kilograms, like go for it, but like make sure you're documenting what you're reporting. You don't want to end up, it's like a factor of, what is it? I don't know, inches to meters. Now I'm a little lost. I don't know how to convert that. And here, I mean, for the most part, this thing is all, I don't need all these extra decimal points. So if I want, I could say 0.0 F, think like that. Yeah, colon 0.0 F. And that colon 0.0 is telling it like how many spaces do I want to the left of the decimal, how many sig figs do I want to the right, and then F is giving me like that it's going to be a floating point number. So now I can do same thing for that density, right? Print. And then now it's keeping track, like I'm keeping track of what my units are, and I'm printing those out like with that output. Really helpful if you're trying to like make a script for something of like, I need you to go through all these Excel files and just print out whatever. There's a mass and a volume in every Excel file. I need you to grab that cell in everything and just print it out. So I have a list of every density from these 100 Excel files that this 52-year-old engineer gave me last week and wants me to go through and manually click on 2 cells and divide the two. And again, I don't need all these sig figs. Like, this is way too many. Going back to that first discussion of like round off error, by the time I get out here, there's no, like, I can't even calculate pi that accurately. So this is way too many sig figs. And also, I only know the volume to within ½ an inch. So really, I've got like 1 sig fig, and then even the pounds is probably like 30. It's not 31.1, it's just 31. So really, let's just go like 1.2 F. 1.3 since it's kind of small. So 0.016 pound per inch cubed. Or I could multiply that by 16. Have it, how many ounces there are. And now it's, oh, but I should change the units, right? Ounces per inch cubed, something like that. And the units look a little better. 1/4 ounce per inch cubed. So every inch cubed is like 1/4 ounce for this box. So that was the first thing that came up. Nobody asked about like, how do I make my print statements look nicer? But I thought it was a good chance to just show you the possibilities. Oh my God, this. There we go. So then other thing that, what was it? Here, when we're looking at sine cosine, so if you're dealing with arrays, the reason to do like math with arrays is that everything works the way that you would expect like math to work on an array. And if you've used MATLAB before, MATLAB by default assumes everything is a 2-dimensional array. NumPy lets you choose how many dimensions you have, but so it's like if I say x is 0, pi, and 2 times pi, then I have this list of 0, pi, 2 pi, but it's a list. So if I try to say, all right, well, let's divide this whole thing, oh, let's multiply it by 2. Like, so that I go 0, 2 pi, 4 pi. I don't get 0, 2 pi, 4 pi, I get 0, pi, 2 pi, 0, pi, 2 pi. Because lists, the way that they work, when you do like multiplication on a list, it gives you like multiple copies and creates a new version of that. But instead, if I call this an array, then I can do like regular math on it. So 0, 4 pi, or sorry, 0, 2 pi, 4 pi, because I took 0, pi, 2 pi, multiplied by 2. The reason for that is that it can also give me if I'm using NumPy arrays with NumPy functions, then those functions take in arrays and give you more arrays. It's arrays all the way down, turtles all the way. And that's pretty cool because then I can change the size of these arrays. So instead of manually putting in like 0, 0.1, 0.2 all the way up to 2 pi, I can start using functions like linspace. Oh, np.np, there we go. And now it'll give me 50 different values of x, and I can take sine of 50 different values of x and do some cool math that way. Or I can tell it, so the way linspace works is start, stop, and this will be up to and including that stopping point, and then the last value is like how many steps that I want. So if I want 11, then it'll give me just 10 equally spaced points from 0 to 2 pi. Yeah. So those were the things that came up as I was walking around. Did anything else come up as you were working? At least those were the things that I talked about that I thought would be interesting. No?
Oh yeah, yeah. And then it goes on for a minute before it's like, yeah, not so sick me out, right? More myself.
All right, thanks a lot. Nice work today, and we'll keep it up on Friday. You too.